Hi, today we're going to talk about the concept of adjacency matrices. An adjacency matrix is a mathematical object called a matrix. It looks like a table of numbers where we keep track of what's located in each position, how many columns and rows in. And the numbers that are encoded in an adjacency matrix tell us what vertices in a graph are adjacent to each other. So if we look at this graph G here, we see we have a vertex 1, which is connected to vertex 2 and 3. Vertex 2 is connected to vertex 3 and to vertex 1. And we also have that vertex 3 is connected to 2 and 1. This graph is totally connected. So if we want to record the adjacency matrix, we're going to put a 1 in an entry I, j if the two vertices I and j are connected by an edge. So, and if not, we're going to use a 0. So in this example, since the vertex 1 is not connected to itself by an edge, and that'll never be the case for the kind of graphs we are looking at, we're going to put a 0 there. But then 1 and 2 are connected, so we would have a 1 in the second column first row to denote these are the same. 1 and 3 are connected, so we put a 1 there as well. Moving down, I'm going to purposely only focus on the upper triangle of the matrix because it's going to be symmetric. You'll notice that because in this first column of the second row, we're supposed to ask, is 2 connected to 1? Well, the answer is yes, just because 1 was connected to 2. And then, of course, 2 is not connected to 2, so we have a 0. 3 is connected to 2. In the last row, 3 is connected to 1, 3 is connected to 2, 3 is not connected to itself. This is the most packed adjacency matrix possible. You'll never have one that's got more going on than this guy does. Alright, let's look at a second example with a few more vertices and not as many edges proportionally. So we're going to consider now the graph that looks like this. We're going to have vertices 1, 2, 3, 4, 5, 6. We could also use letters. It's just going to be simple for art. And I'm going to draw the cyclic graph on these vertices as such. And then I'm going to also add in a couple of extra intersections. Couple extra edges, but not all of them. Notice, for instance, 2 is not connected to vertex 4 or to vertex 6. Every vertex has degree 3. Okay, so what would the adjacency matrix look like? Well, it's going to be kind of big. I'm going to use, just for my notation purposes, I'm going to kind of draw in the rows and columns so I can keep it straight. But usually you don't need a grid when you're doing a matrix. 1, 2, 3, 4, 5, 6 rows, and I need 1, 2, 3, 4, 5, 6, not enough space there, 6 columns. Alright, as before, we're going to have zeros down that diagonal because we don't have vertices adjacent to themselves. There's no edge from a vertex to itself. We don't have any of those loops appearing in our graph. I'm going to just fill in the top triangle of the adjacency matrix because the bottom part will be the same. So if I look at vertex 1 in the first row, vertex 1 is connected to vertex 2. It is not connected to vertex 3. Vertex 1 is connected to vertex 4, my bad, sorry, but not to vertex 5. And it is connected to vertex 6. Moving down, vertex 2. Vertex 2 is connected to vertex 1, and it's also connected to vertex 3, and it's also connected to vertex 5, but not to 4 or 6. Alright, next we have 3. 3 is not connected to 1, 3 is connected to 2, 3 is connected to 4, not to 5, but to 6. Next we have 4. 4 is connected to 1, but not to 2, to 3, and to 5, but not to 6. Vertex 5 is not connected to 1, but it is connected to 2. It's not connected to 3, but it is to 4 and 6. And lastly, and really to get this last row, notice that I already have a column that tells me the relationship between every vertex and vertex 6. So I'm actually just going to copy that column down horizontally. A 1 here becomes a 1 in the first column. The 0 in the second row becomes a 0 in the second column. The 1 in the first row is a 1 in the third column. A 0 for 4 and a 1 for 5. So here we have the full adjacency matrix for this graph. Now you may be wondering why these are useful. Well, it turns out that it's a very quick way to encode just the shape of a graph, and when we start talking about isomorphisms, it'll be good enough to use graphs only from that context. So just to give you a little more practice, I'm going to draw 2 last graphs, and I'm going to encourage you to look at the answers. So here's a graph where we have some vertices that are totally isolated. We're going to have vertex S, T, U, P, Q, and R, and they're going to be connected as shown. Alright, so let's build the adjacency matrix, and for sake of good ordering, we're going to use alphabets to do this. So we'll have a P row, a Q row, an R row, an S, a T, and a U, and we'll have a P, Q, R, S, T, U column. Again, I can pop my zeros down the diagonal because vertices aren't adjacent to themselves. So let's start with P. P is adjacent to Q and also to R, but not to S, T, or U. Q is adjacent to P and to R, but not to S, T, or U. R is adjacent to P and to Q, but not to S, T, or U. Alright, now STU. S does not have any relationship with P, Q, or R, nor with T, but it is connected to U. T isn't connected to anyone, so there's a whole row of zeros. And U is not connected to P, Q, or R, but it is connected to S. Notice here when we get these big blocks with no numbers and all zeros, those correspond to places where you have sets of vertices that don't relate. It tells you that there are these two connected components. The STU is in a separate block from what's happening with P, Q, and R. Pretty cool, huh?